Okay, so yeah, think what we said here, right? We talked about, let's review what we talked about day before yesterday, right? So we had kind of a working definition of continuity, which is a really good one. Graphically speaking, a function is continuous on an interval, on a closed interval, if I can put my pen down at a f of a and graph the function all the way up to b f of b and never pick my pen off the board, right? So that's easy. But what we had to do, we had the challenge of trying to come up with some criteria for dealing with mathematically that would match that graphical criteria, some analytical, mathematical, symbolic criteria. And what we ended up having to do, remember, is we had to break this into two steps, sort of. We had to break it into continuity on an open interval, right, which means ignoring the endpoints for all values of C that are between A and B. All we had to do was show that for every one of those infinite points, they met the three criteria for point continuity, right? And what was point continuity? We said that a function was continuous at a point if we couldn't have any vertical asymptotes, for example. Well, okay, we fixed that by just saying the function has to exist at C, right? Well, we can't have any holes in the function. We can't have any breaks in the function either then, all right? So how do we fix that? Because we could have a break in the function where the function is still defined at the break, right? So that means that the limits, the regular two-sided limits have to exist. Ants approaching from both sides have to anticipate stepping on the same place. And that left us one loophole, right? That left us the loophole of, well, what if you had one point that had been displaced? So the function exists at C, well, that's supposed to be C, you get it though. If the function exists at C and the limit exists, well, we ducked under each of these separate criteria. But then if we just said, okay, well, if the value of the function has to equal the value of the limit of the function at C, then we couldn't do this, right? And we fixed everything. So those three criteria for point continuity, they take care of all of the infinite points between the endpoints, right? But we had a problem with the endpoints because we couldn't really make the limit work there, right? Because a limit, as we've always defined it, remember, means that ants approaching from different directions have to agree on where they anticipate stepping when they get to the value of C, right? And we can't do that with an endpoint. How are you going to walk from the left at a left endpoint? There's no place for the ant to step, right? And so we came up with a new vehicle for that. We said that, let's see, we said, next page, I guess, yeah. We came up with the idea of a one-sided limit. Okay, we can do a limit from the left or a limit from the right. We could say, okay, yeah, we could make this work if we invoke at the endpoints these special limits. We'll replace the two-sided limit instead with a one-sided limit. So on the right endpoint, if this is our interval, on the right endpoint, if we just say our previous definition of point continuity will work there if we only expect the ant to walk from the left, right? You can't walk from the right anyway. And it's okay, isn't it? Because think back to by having this two-sided limit, all we were really trying to do was prevent there being any breaks in the function, right? But how could you have a break in the function at the endpoint, right? That, by definition, could only apply to the interior of the interval, right? A break in the function would necessitate having some function to the left and some function to the right, or it's not a break, right? You see what I'm saying? Okay? So really, we don't need the same kind of criteria at the endpoints. We just need criteria that only deal with the possibility. The only way that endpoints could get screwed up is if they did this, right? if we did something like, oops, gosh, this is boring. I need to get a new pen. I think that's my problem with this board. The only way the endpoints could get screwed up is if we did something like this, right? If there were a hole at the endpoint and we displaced that one endpoint, because there is no function to the other side. If there were, then that would be a break. But there's no function over there, right? So we don't have to worry about that. So then we don't really need as tight of criteria for the endpoints. We could just say instead, at the right endpoint, for example, if the function exists and the limit, the one-sided limit exists, and they agree, we're fine, right? The limit of the function as the ant approaches B from the left, which is what that says, right? That's what that little superscript means next to the C. That's telling us where the ant is walking from the negative direction. If that limit exists and the function exists and they're equal, that takes care of that endpoint, right? What about on the other side? Same idea, right? On the other side, we'd have to just say same concept, but now as the limit as the ant approaches A from the right would have to exist and equal f of A, okay? And so, you have your books with you? I don't want to write all this down, so let's just look at your book. If you don't have one, just share one with your neighbor. Quickly go to page 70 and look in the middle of the page at definition of continuity on a closed interval. What's that? So actually, before you do that, look up to theorem 1.10, existence of a limit. And this is one I will write down. I want to just briefly talk about this. Not complicated, but could we tighten up our previous definition? Oh, I haven't got you a textbook yet, have I? I'll get you one. Remind me. Of course, I should have probably thought about that. I'll get you one today. Can we tighten up our previous definition, working definition of a two-sided limit? We talked about it in terms of ants, right? That's probably not going to fly when you get to college. Probably going to have to maybe. That's all right. The ants are just illustrative. We said that if you anticipate stepping on the same place when traveling towards that point from both directions, then that works as a limit. Well, now that we've got this idea of a two-sided limit, could we maybe write this in a more rigorous way but carry the same meaning? How could we say, don't cheat, don't look in there for a second. I'll see if you guys can just come up with this on your own. So we want to say, this makes sense. We want to say that the limit of f of x as x approaches c equals L, but carry that same concept in our definition of a limit. That is, ants approaching from the left and the right must agree where they anticipate stepping. How could I use...
Have the subscript have positive negative.
Okay, so so this is going to be, we have to have our, we're going to make our supposition here, or our hypothesis, right? And this is going to be our conclusion if that's met, right? If what? You tell me what to write. The limit of f of x.
As x approaches, what can we do the superscript plus minus c?
Yeah, well no, we have to do just one at a time. So as x approaches c from, let's say, the left, equals what?
The limit of f of x is that x approaches c from the right.
Okay, equals the limit of f of x as x approaches c from the right, and they're equal to L, then that has to be true, right? If the two, in other words, we could summarize that by saying if the two one-sided limits exist and agree, then the two-sided limit works, okay? Now the beauty of this is, though, as we move into the future, this isn't exactly the topic for this exact moment here, but in the past, when we got something, we'll talk more about this later, but what if we took something like the limit of 1 over x as x approaches 3, as x approaches 0, sorry. That gave us 1 over 0, which was no limit, right? Okay, so this might be a great thing. if we said something like, as x approaches 0 from the left, maybe we could actually say something more specific than just no limit. Okay, we'll get there. Okay, take a look at page 70 in the middle then. Definition of continuity on a closed interval. I just want to talk through this, and I want you to get used to reading rigorous mathematical definitions like this and just make sense of this. This is a big deal. A function f is continuous on the closed interval from a to b. Summarize, what's that mean, closed interval from a to b? The line segment, well, not necessarily a line segment,
The segments.
but from the value x equals a all the way to the value x equals b, including the endpoints, right?
Yeah.
So we're saying we're including the endpoints. So I'm setting my pen down at a f of a, and I'm drawing it all the way over to b f of b, right? That's true. It's continuous on that closed interval if, two things, it's continuous on the open interval from a to b, right? And we take care of the endpoints. If the limit of f of x as x approaches a from the right equals f of a, and the limit of f of x as x approaches b from the left equals f of b. Okay? Then we say the function f is continuous from the right at a and continuous from the left at b. Okay? So those are the parts, two parts. If it's continuous on the open interval, which just means that, right? And remember what we said also. These three criteria, as this textbook and a lot of textbooks present it, really could be summarized by number 3. If you remember number 3, it's a giveaway of the first two, right? All we know is that the limit of f of x as x approaches c has to equal f of c for all the points between a and b, right? Okay, so that implies that, well, that statement wouldn't make any sense if the limit didn't exist and the function didn't exist at c, right? So I think you can almost skip those first two, right? Okay? So let's try a couple problems that sort of relate to this. I want you to right here. Okay, I want to do one like this. Stare at that for a second. Think about it. Talk about it with your neighbor. Let's be prepared to rigorously discuss this. Figure out what this limit is.
Those commas.
Those are commas.
Okay.
Yeah. So maybe the first thing you want to do with your neighbor is remind yourselves what that notation even means when I define f of x like that. Okay? Okay, so what's our deal here? So talk to me. You discussed this a little bit. Some of you have evidently discussed it telepathically, but I'm trusting you did that. So what does this mean when I write a function this way? What do I call that? Piecewise function. So it's defined in pieces. This is the piece that defines the function on this domain. This is the piece that defines the function on this domain, right? So when I want to look at the limit here as x approaches 3 Why is that maybe a little bit problematic?
The second one can only be greater than 3x.
Okay, but that's okay, because when I'm taking a limit, do I ever actually get to the point? No, I don't, so that's okay, right? The limit is all about where you anticipate stepping, not where you actually step, right? But what's the, I mean, I guess maybe that was a vague and probably a bad question.
Shouldn't the first thing that we do is just plug 3 into the two equations without even looking at the x equals whatever nonsense?
Okay, I would argue that's not the first thing, but the second thing you should do. Because doing that is really a consequence of the first thing you gotta think about. We just talked about the definition of a two-sided limit. So if this limit exists and has a value, what has to be true?
The value has to. wait,
Okay,
the
true, but there's
Oh, the
more
limit
to it.
has to exist. No.
Okay, you're right, but there is a sidedness to limits, right? The limit has to exist and have the same value from both sides, right? Okay, so on this one right here, you mean? Okay, that's okay, because we never actually have to step on 3. We just have to approach 3. But if I wanted to be very rigorous about this and do this in a mathematically tight way, which I want you to be able to do, how am I going to get this answer? Or come up with the answer that it doesn't exist? Well, no, we don't want to graph it. We want to do this analytically. We want to do this analytically. How did we say that? We just talked about a second ago about what the definition, really our more rigorous definition of a limit means. The limit of f of x as x approaches c equals L implies that the limit from the left and the limit from the right exist and share the same value.
So why wouldn't we just, the first thing we do, find the limit of both
Well,
of these?
because-
We would, but finding the limit means we've got to write that as a limit, right? So we're going to say something like, let's take this case up here. This will be our blue, right? We're going to deal with that part in blue. Is that going to be a left side, a limit from the left or a limit from the right? That's going to be a limit from the left, isn't it? Right? Because this is the function that exists for values of x that are less than 3. I don't even care that it's equal to 3. What's important to me is that part, right? Because as I take a limit, I don't ever get to 3 anyway, right? The equal sign wouldn't have even had to have been there, okay? So then, the limit of f of x as x approaches 3 from the left is equal to the limit of this piece, right? The limit of x plus 2 over 2 as x approaches 3 from the left. Okay, Jonathan, what's that going to be? 5 over 2, isn't it? Does it matter that we're approaching 3 from the left? Well, I mean, what value are we still approaching? 3. So when I evaluate the limit, I'm still going to plug in a 3, right? This just tells us the directionality of my approach. That's it, right? I still get the answer of 5/2. So this is going to be the red piece of the limit, or the function, right? Let's take that limit. From what direction will I be approaching 3 when I'm walking on this piece? From the right, okay? So I got the limit of x as x approaches 3 from the right equals the limit of this function. 12 minus 2x over 3 as x approaches 3 plus. So what am I going to get for that? So I'm going to get 12 minus 6 over, so I get 2. Everybody agree? So what's the deal?
They're not equal.
They're not equal. So does the limit exist? No, doesn't exist. Okay. Do you see that I still, and this is kind of important, do you see that I could have changed this problem in this way and it wouldn't have really affected how we approached it at all? Right? In the same way that previously we said that if we had a function that had a hole in it, then I could still, if that's at C, doesn't matter. The limit still exists there. right? Even if the function doesn't. Because the limit's about what we anticipate stepping on, not what we actually step on, right? Okay.
So what does that mean for the graph?
Say it again?
What does that mean for the graph?
So it means there's a break in the function. So if we were gonna graph this thing, what we would have gotten is, it would have looked like, essentially like this.
Do all
The
graphs-
blue piece would have been a line with a slope of 1/2. And the red piece would have been a line with a slope of -2/3, and they would have missed each other. Okay. It would have looked something like, at 3, it would have gone, well, oops. I want to be 10, a little better, it would have been more like this. Whoops. Something like that. Right? Okay, another one. Okay. How much time we got? 5 minutes, okay. We have time for one. I feel like, I wish I had time for 2. I got time for 1. This will work. Maybe we'll have time for 2. I'll start with an easy one. Okay, this is really not a calculus question at all. This question you could have done last year or the year before.
Trying to find where 0 is.
It's 1/x minus 5.
Okay, so what'd you do?
You factor the bottom, then you cancel out the top and the bottom. The parentheses, because that factors out the x minus 5 times x plus 2.
Okay, so you factored the bottom first though, right? So you said we had x plus 2 over x plus 2 times x minus 5, if I factor the bottom, right? Okay, now we gotta be careful with this one. That's really the only point of doing this problem is to address this one issue. We're talking about the function f of x. So are there any places at which f of x is discontinuous? Yeah, there are 2. -2 and +5, right? So it's gonna be wherever we end up having, where is the function gonna be discontinuous? Really, a function is gonna be discontinuous only in places where we have breaks in the function that are caused by a piecewise function, or we have poles or asymptotes that are created by violating our rules for real numbers. There's really only 2 laws for real numbers, and we've talked about them before. We can't divide by
0.
0, and we can't take an even root of
Odd number.
a negative number, right? Can't take an even root of a negative number. Barring those 2 things, there's really no problems unless there's some, like I say, unless there's some wacky piecewise function where the ends don't match up, or we're given some artificial restrictions on the domain or something like that, right? But really here, we just end up getting, when I plug in x equals -2 or +5, I get zeros on the bottom, which is forbidden. So I know those are places where the function cannot exist, and therefore it's discontinuous. I'm gonna jump ahead a little bit. We're gonna come back to this in more detail later, but I wanna give you something important just so you see it more than once. The nature of those discontinuities are very different though, right? we've dealt with limits like this before, and we said that if we were gonna take a limit of this function as x approached -2, we could get an answer, couldn't we? Right? Because we could cancel those factors and we could trade f of x for a new function, call it g of x, that agrees everywhere but one point. We're just gonna fill in that hole, in other words, right? So that tells us something important. Whenever we have a common zero of the top and the bottom, that always corresponds to what kind of feature on a graph? A hole, right? But if we get a value of x that is a zero of the denominator and not the numerator, that's much, much bigger deal. What's that? That's gonna, if I evaluate this at x equals 5, I'm gonna get some number divided by 0, which is always a vertical asymptote. Okay? So you see the difference there? It's discontinuous in two places, one of them very minor. One of them is a hole, the other one is a big time issue, that's a vertical asymptote. Okay? That's a good place to stop for today. All right.
And so we're gonna-
All right, you guys take a couple days off. It's been a lot of work.